welcome to our workshop today on the application of heat pumps in Saskatchewan. My name is Tom Atkins. I'm a professional engineer and a retired mechanical engineer that I spent most of my career in the consulting business. And I'm going to be your moderator today. So first off, a big thank you for taking time to attend the workshop. It's intended as a session where we can just increase everybody's understanding of the topic of heat pumps. And my experience in consulting, where I was in many sectors, one of the through lines of it was energy efficiency and sustainability, and in the last few years, decarbonization. So we're going to hopefully today increase your understanding of what impacts heat pumps can have, what are the impacts of our location, be it utility related, climate related, on the heat application of a heat pump system, and to just get a broader understanding amongst ourselves in the workshop portion of common questions that you might have and some experience from all of you. So this is workshop came out of a series of decarbonization symposia that the University of Regina hosted over the last year and a half. And it was, although the university hosted it, it was really organized by an ad hoc group that included quite a few groups, mainly the City of Regina as a partner, along with SaskPower, Sask Energy, and a few other interested parties. So when we did the buildings symposium, one thing that came up in several of presentations were the topic of heat pumps, and there was seemingly a lot of misunderstanding or lack of understanding on how they might be applied, specifically in the small residential and light commercial sectors. So that's the genesis of the workshop. And so first off, I really have to thank the University of Regina. They've had several groups that have been instrumental in organizing this workshop. We have the Faculty of Engineering and Applied Science. We have the Sustainability Office and the Vice President of Research's office. We also want to thank the City of Regina for kind of spurring us on to get this done. It's one of the things that they were very interested in, and specifically how it ties in and relates to their energy and sustainability framework. And we've also had support from the Regina and Region Home Builders Association and the Mechanical Contractors Association of Saskatchewan, and to help promote. And they actually gave us feedback on how we should run this today. So without further ado, I just want to introduce Dr. Raman Paranjape from the university to bring greetings from the university.
Right. Thank you, Tom. Yeah, my name is Raman Paranjape, and I'm here to thank you for coming and bring greetings from the university. But I'll begin by actually doing a land acknowledgement. So the University of Regina is situated on Treaty 4 lands with a presence in Treaty 6 territory. These are the territories of the Nihiwa, the Asenapek, the Dakota, the Lakota, the Nakota, and the homeland of the Métis. Today, these lands continue to be the shared territory of many diverse peoples from near and far. We recognize the contribution that engaging in reconciliation brings to our lives as a campus community that is situated on these lands. The university is committed to making reconciliation a part of all interactions amongst Indigenous and non-Indigenous students, faculty, and staff. So to continue with my greetings, I guess I'm pleased to see that there are so many people from small businesses, you know, mechanical contractors, home builders, whatnot, that are in the audience. I think our registration is up to 88. So we're quite happy about that. I do want to put a plug in for the university in the sense that, you know, you are all out there working hard, trying to solve problems, trying to be successful with your business. The university, and particularly the Faculty of Engineering, is open to help, to support you. I haven't seen Fatima from my tax. I don't know, Fatima, are you in the room? Not yet, I guess. But there are programs that are available to help small companies to solve problems that you might have in your day-to-day that might involve having some research, some analysis, some work with students, that sort of a thing. So I mean, we hope that this will be very educational and interesting to our audience, but if there are issues that you have, you know, my email is in the email that was sent out. Please contact me. We will try to figure out how we can help you from the university. The university is not an ivory tower. It is here for our community. So with that, I will hand it back to Tom. Thank you very much.
Thank you, Raman. And now from the City of Regina, I'd like to introduce Robbie Humble. Robbie is the Manager of Sustainable Energy and Adaptation.
Yeah, hi everyone. I don't have a lot to say other than just, reiterating it's really awesome to see everyone here. We've been working with a lot of these folks, as Tom was saying, in terms of the previous symposium, and also some of you would have attended the November Net Zero Renovation Boot Camp that we hosted in partnership with the Home Builders Association. And so it's awesome to see this sort of continuing conversation, and we're grateful to be a part of the conversation around how we can be supporting industry and helping industry support residents when we're making decisions about retrofits and renovations to our buildings and looking at net zero new construction. As Tom mentioned, that's a big part of our energy and sustainability framework and meeting the community's net zero targets as well. And so just wanting to say thanks for coming. And I glanced at the registration as well, and awesome to see a lot of diversity of folks here from different backgrounds. And you don't need to hear more from me. I'm really eager to listen into the discussion today and hear you know, what you're seeing and how we can support you in taking this work forward. That's it. Thanks so much.
Thanks, Robbie. So as I said earlier, heat pumps are receiving a lot of interest, specifically in the media and in the general public, and some within industry. Any of you that are mechanical will understand that heat pumps have been around forever. I think when Jerry Belangina spoke to the City Council during the discussions around the energy framework, we said that, you know, when I was in university, which was a long time ago, and when Jerry was early in his career, heat pumps were already around. The biggest difference is that there's been lots of technical refinement over the years to make them operate more efficiently and better, and in different applications. But the technology, basic technology, is nothing new. Certainly, one of the things that we are cognizant of is the variation of opinion, and we want to make sure that people are informed. There's lots of different ways to apply equipment, and there's no one right way. So this is not intended to be a sales pitch for technology. It's meant for people to understand how equipment would be applied and what the implications of those are. What implications for the installing contractors, the implications for the homeowners and or businesses that are going to pay the utility bills, implications for the utilities that are connected to that equipment, and so on. So what you should learn from this event are the impacts that heat pumps can make on decarbonization, the relationship between climate and how a heat pump works. And also the relationship between the utility energy mix and the GHG footprint of that. The utility mix is impacted, what some trends in product development and other technical aspects are, and some discussion on short and long-term economics. Although this is primarily not an economic presentation, we do know that economics comes into everything. And also we're very happy to have reps from Sask Energy and Sask Power to talk about what's going on within their organizations, as they're quite central to this. Now, the last half of the event, we're going to try to move it along. The last half of the event is meant to be an open workshop where you can ask questions, we can ask questions of you, and we can just share knowledge. So it's an active participation portion, and I hope you're all are all up to it. We're also going to talk about just peripherally about maybe some of the other applications of heat pump type technology and where you might see it come up. But we really want to focus on those questions. And I should also say, as you saw me stumble at the start, we are recording this event. That's a practice that the university has done for our symposia. And so eventually the recording will go back up on the website and you can refer back to it. Or if you so choose, you can share it with your colleagues that haven't been able to attend. So without further ado, we're going to move on to the first presentation. We have Matt Dipple from Airtight Engineering, and he's going to give us a little bit more of a talk around the design aspects of heat pumps.
Great, thanks, Tom. Now, let's make sure I can get my slide deck up. Okay, perfect, great, awesome. So just a brief introduction of myself. Actually, we can skip that because Tom already did it, but maybe just to say that I work with a small firm here in Saskatchewan called Airtight Engineering. We focus on energy modeling. We also do mechanical design, and we really spend a lot of our time in the high performance building space. So we actually see a lot of heat pumps in our work. And when we're doing design work, either here or other parts of Western Canada, a lot of our clients are requesting heat pumps, in fact. And so they're driving that for us. So it's something that we get to work a lot with. And so part of why I'm here to share a little bit of my experience with you and hopefully learn from yours as well. So just a brief outline. First, we'll go through what's all the hype about. We'll talk really briefly about that because I'm sure many of you are already somewhat familiar with the concept of a heat pump and why it's beneficial. We'll talk about a few frequently asked questions in terms of heat pumps here in Saskatchewan. And then we're going to dive into a few design considerations. This is going to be really high level because Tom said he's going to run and tackle me if I take longer than 15 minutes. So, or at least tackle me with his eyes. And then I'll mention just at the end of my presentation, we'll save the questions and discussion for our sort of roundtable session or our interactive portion. But I'll talk a little bit about some resources that are out there for you as well to take you further. Okay, so what's the hype? Three things come to mind. The first is efficiency. With a heat pump, because we're moving heat instead of generating heat, we can break the 100% efficiency barrier, right? If you're just producing heat by burning a fuel or burning electricity, you can't get past 100% efficient. With a heat pump, we're now moving heat from indoors to outdoors or outdoors to indoors, and we can get 200, 300, 400% efficient. So that's one of the big things. Also versatility. The next slide, I'm going to show you all the ways that we can use a heat pump. And then finally, opportunities for electrification. So heat pumps give us a path to at least electrify some of our heating, if not all, depending on the case. And we'll dive into that a little bit more. We're focused a little more on residential, but I think this is interesting just to see the energy use in a typical Canadian home and where a heat pump can be slotted in to save some energy. So we've got lots of areas of our house that heat pumps can be used. Space heating, water heating. We'll see some appliances like a heat pump dryer, and then also cooling, obviously. So we'll be focusing mostly on heat pumps for heating and cooling, but just a reminder that we find heat pumps in other spots in our buildings as well. So if you're in a house, your refrigerator is a heat pump, your deep freeze is a heat pump. You can now get heat pump hot water heaters. So there, that picture in the middle is a hybrid hot water heater. You can get heat pump dryers as well. And so they're quite versatile in the ways that we can use them. I think personally, I think heat pumps are one of our top inventions, aside from maybe libraries and maybe the sandwich or something like that. But heat pumps are certainly up there. So again, talking about efficiency, this is why we're so excited about heat pumps. Is an air source heat pump, its seasonal efficiency might be around a COP of 2 here in Saskatchewan, so 200% efficient. For a ground source heat pump, might be more like 300% plus in Saskatchewan. So we get to really cash in on breaking that 100% efficiency barrier. And then for water heater, just showing that same thing. So the coefficient of performance, which we can think of as percent efficient here. So just looking at some other, it looks like I didn't update my natural gas tank and tankless numbers. Those could go a little higher as well. I thought I had. And here's another spot. So I mentioned heat pump dryers. This is stolen from SaskPower's website. Well, not stolen because I cited it at the bottom, but you can see that dryers are one of our top appliances in terms of energy use in the house. And they're a spot where we can actually slot in a heat pump. Heat pump dryer is going to take a bit longer to dry, but it uses half of the energy or less of just a conventional electric dryer. So another great application. Okay, so that was your motivation, your primer on why we should care about heat pumps and some of the benefits they can have for us. So let's talk about some frequently asked questions. First one, this is maybe a popular media question, is do they work in Saskatchewan? And the answer is a resounding yes, they do. I just put 3 random projects that we've done design work on that have been built, that have heat pumps. They're in Saskatchewan. They are operating, working just fine. So we've got one up in Cumberland House, this one here in Saskatoon, one in Montreal Lake. They've all got heat pumps as their primary heat, and then some type of backup heat. So in Cumberland House, they actually have a wood pellet furnace because they don't have natural gas access. The one in Saskatoon, it's a passive house project, so it uses so little energy that they just went with backup electric resistance. And then Montreal Lake is actually, it's a greenhouse, and they don't need backup because they're only running 3 seasons. So these are all air source heat pumps we're talking here. I will note that ground source heat pumps work in almost any climate, minus maybe permafrost conditions, because that ground temperature is much more stable than the air temperature. Modern cold climate heat pumps can work down to -25, some of them down to -30. Some of you may be used to the older generation of heat pumps that kind of petered out at around -15. And even at -15, they were getting a very low capacity that they could actually provide heating. Whereas our modern cold climate heat pumps can just do much better than that. And so that's something that we need to sort of, I guess, relearn if we're familiar with those older versions of heat pumps that what should the saying be? You know, this is not your grandmother's heat pump, right? This new generation has a lot better capacity and a lot better COP at cold temperatures. And then this is in honor of Doug here. I also included a graph just because I know Doug really likes graphs. So we happen to have some monitoring data. So this is some electricity monitoring data from high performance project we did in Saskatoon. So it's got primary heating with heat pump. Backup is electric resistance. Again, it's a pretty efficient build. So that's why they went with that as opposed to gas backup. And we can see this past winter season, the blue line is temperature. The little red line is the heat pump. And then the green is the backup electric resistance. So we can see a couple periods in the winter where that's coming on, namely that huge cold snap that we had for a few weeks in January. But I just show this to highlight that point of, yes, that heat pump is running. It's actually running even down at some of those really cold temperatures below its sort of rated temperature, even though it's also got some backup heat with it. Next question, will a heat pump save money and emissions in Saskatchewan? So I did a little bit of analysis. I looked at a few different scenarios. So I looked at natural gas heat with a high efficiency furnace as sort of my base case. Then I compared a heat pump with natural gas backup and a heat pump with electric resistance backup. I also looked at three types of house. One is sort of a pre-1980s house, so a higher heating load. One is a modern efficient house, so lower heating load, and then a modern best-in-class house. This is like a very efficient house. There's my little heat pump symbol. Okay, so yeah, we also looked at resistance backup. So the first question, cost. Will it save money in Saskatchewan? The answer is it depends. It's not totally clear. So if we just look purely on fuel consumption costs, today, your heat pump would need to have a minimum coefficient of performance of above 7 to actually save money in terms of the operating cost, which no heat pumps have that. So sorry, out of luck. By 2030, you would need a minimum COP of around 3.5, 3.6. So now a big piece of that is increasing carbon tax. So gas is becoming more expensive because of the carbon tax. So using that projection versus a heat pump, which is switching some of our heating to electricity, what does that look like? So I was looking at some different models. A lot of heat pumps can do a COP of 3.6 down to maybe 0 degrees, maybe -5, a couple to -10. But if you're heating above those temperatures, then so really that shoulder season heating, you would be able to get kind of performance. And so bills that are in line with what you'd be paying for gas. I put also the best in class house. So I put pre-1980s house. You're probably going to need gas backup. That's going to be your best bet. Modern efficient house, kind of some question around it, but really you're probably not going to save too much, and you'll probably end up spending more. And then the best in class house, that's where we get to the point where the base cost of the utility might start to impact things more. So you're paying not only a consumption cost for the amount of gas you would use, you're also paying a base cost for having your service hooked up. And so if you have a house that's efficient enough that you're using a very small amount of fuel, that's where you get to the point where that base cost could start to factor in. There's a lot of other considerations. If you don't have your gas hooked up, that means you're going to have to heat your water with electric. That's going to be an added cost. We were having a good conversation in the days leading up to this, talking about sort of capital costs of utilities and how right now that's shared between gas, SaskTel, and SaskPower. Well, if you don't get a gas service hooked up, how does that affect your initial cost for those other utilities? So there's certainly complexity around this cost question. This is a question that has a much clearer answer. So will it save emissions in Saskatchewan? Right now, the answer is no, because we still have a lot of fossil fuel on the grid. So it's not going to save emissions if you switch your heating to a heat pump, but very soon it will. So by 2026, 2027-ish, we're projected to have SaskPower is doing a great job of reducing the emissions of the grid. And so that's when we're expecting to see greenhouse gas savings from a heat pump. And based on some rough calculations, on some very rough projections, by 2030, you might be saving a half of your greenhouse gas emissions to maybe 2/3 for your heating. So some takeaways of those questions. Carbon, we're really reaching an inflection point for heat pumps in the next couple of years. Cost, more complicated. We do have to start thinking over the lifetime of our system though, right? Even if it doesn't make sense carbon-wise to install a heat pump today, that piece of equipment is going to be around for 15, 20, 25 years. And we've got lots of other cases that we could go into and look into further on both of these questions as well. One thing I do want to highlight is that heat pumps are important. They're a great piece of technology, but actually the biggest impact that we can make is improving our building envelopes. That should really be if you've got a client who comes to you and says, hey, I want to do right by the environment, I want to install a heat pump. Your first question to them should be, have you upgraded your windows? How airtight is your house? Have you added insulation to the attic? Because those are really the sort of the primary drivers for efficiency. And then the efficient mechanical system is a great second step after. How am I doing for time? Okay, all right, sounds good. So here's just a few of the things that we could see for improving our building envelope. I just want to touch on a few design considerations. I will, what's probably worth talking about? We've got lots of design considerations with heat pumps. I'll touch on this, which is just in Saskatchewan, cold climate heat pumps work. We do need backup heat. So we do need to make sure that we've got either natural gas or electric resistance or something else as our backup heat source. And it's also important to avoid oversizing on a heat pump because often we're cooling with a heat pump as well. We want to make sure that we don't oversize for heating and then run into an issue of having an oversized cooling system. So that's an important design consideration. And I would just, the other big design consideration I'd highlight is they're different than fuel-fired appliances in that their capacity changes with outdoor temperature. So if it's -30 outside, it's a lot harder for that heat pump to generate or to pull heat from outside than if it's -5. Whereas a furnace, if it's 60,000 BTUs, doesn't matter what temperature, right? It's 60,000 BTUs. Okay, so I think that's probably all we've got time for design considerations, but just, I wanted to touch on this for resources. The US Department of Energy is doing a ton of research right now into improving heat pumps. So they're just wrapping up a residential challenge and they're just starting a commercial building heat pump accelerator challenge. So this is something to watch for. We're already seeing residential products hit the market, and in the next 3 years, we'll be seeing those commercial products hit the market too. So I think that that's a good spot to end.
Just one last resource for sizing.
Oh yeah, yes.
Intercan has a very good site related to heat pumps. So sort of best practices and sizing guides. So that's a resource that and when you get these slides, you can look at all the resources that are
For
available.
sure. I made some hyperlinks in the slides so you can check out those hyperlinks after. Great, thank you.
Thanks to Matt. Our next speakers are going to be a double presentation from Sask Energy and Sask Power. We have Hattie Raman from the Sustainable Energy Solutions at Sask Energy and Caleb Granite from the Customer Strategy and Solutions Group at Sask Power. So take it away.
All right, good afternoon, everybody. It's good to see such a big turnout. Sask Power and Sask Energy has been looking at heat pumps for quite some time, and we realize there's been a lot of, I want to say, confusion in the media and otherwise, and even on what our role necessarily is for technology research and stuff. And we thought we kind of partnered up and did a group study on heat pumps, and we do a lot of customer facing stuff, energy efficiency programs, customer grid reliability help, things like that. So we wanted to try to just create some customer education material for residential and commercial customers on this topic. And we did make this fancy group logo. We had no website logo, so we kind of combined our logos the other day. So Sask Power Customer Strategy and Solutions Team, that's who I work with. We do several programs. Our primarily function is to do technology research, reduce grid strain and improve reliability, provide energy efficiency programs, discounts, things like that, pairing with other federal or provincial programs, as well as provide a lot of customer education and customer experience. And so we have all of these programs. I won't go into detail today. You can find them all on our website under programs. I would like to announce we just launched the Commercial Energy Optimization Program. So I think that should be important to all of you in some aspect. And this program involves energy auditing of commercial buildings and can involve some incentives potentially in the future for implementing energy efficiency products and measures into those buildings.
Oh, first of all, this is not my real voice. I had a sore throat, so I apologize in advance for that. So like Caleb said before starting my talk about the programs we have, we're developing heat pump material for our network members and also for our customers. And I would like to get your feedback as well to see like what kind of material you're looking for. So we have feedback from our customers and network members and everyone to influence the material we're preparing. So we also have like rebates program at Sask Energy. Some of those rebates program are 10 years old. Most recently, we have developed a Home Beyond Code program, which targets the new homes to be built to a higher tiers in National Building Code. In addition, we're also working and investing in emerging technologies. So with this, we are trying to help our customers to reduce their energy bill as well as their carbon emissions. So some of these technologies are gas heat pumps. So this is a heat pump basically, but works on natural gas. So their efficiency, energy source efficiency could go up to 160%, but a normal efficiency of 140% is something that they do achieve it. We also work with a small scale carbon capture utilization and storage, as well as working with other utilities for have a low carbon gases, working on renewable natural gas and hydrogen. So, and Sask Power and Sask Energy are partnering for some of those programs. This includes a list of programs over here. And we understand that partnering Sask Power and Sask Energy and utility in general would make sense because it helps the customers and also program to be more cost effective by aligning our objectives. So I just want to mention like a gas heat pump in general over here. So gas heat pump, similar to heat pump, is not a new technology. They have been around for many decades, but the application in heating is fairly new. So different types of gas heat pumps are available. So 3 types are absorption heat pump, gas engine, and thermal compression heat pump. Their efficiency is between 120 to 160%. Absorption heat pump and gas engine heat pump are commercially available for commercial sector, and absorption heat pump are commercially available for residential sector. So we are also planning to have a couple installation of gas heat pump very soon this year in residential sector. And we had like demo project with thermal compression heat pump in our training center in Saskatoon. So I just want to end my talk with this graph over here, which shows the primary residential heating fuel source by provinces in Canada. And this graph is taken from a report done by ICF for Canadian Gas Association. As you can see over here, half of the Canadian provinces are relying on natural gas as a primary source for heating. And this heating consumption, or this natural gas consumption, is quite considerable in summer, in winter, considering our cold winter condition. However, like heat pump are more beneficial in a milder climate, in warmer climate, and in like areas when natural gas infrastructure, they don't have lots of net access to natural gas infrastructure, but still natural gas heat pump are also a good option for people to use. And yeah, I think that's all I wanted to mention. Do you have anything on this slide?
Just a brief mention of that, economic considerations. I don't have anything specific, but the difference between gas and electric rates will have a huge impact on the uptake of heat pumps anywhere. We're not recommending either, but like if you do go somewhere, that's one of the biggest considerations besides emissions. So Hadi and I took several scenarios, as you can see, natural gas, supplementing, and then heat pump. We have this 140% efficient natural gas heat pump. That's for the absorption one Hadi was talking about earlier. And then we have heating oil with the heat pump, and all the other scenarios are with the heat pump. So where it makes sense from our point of view at this time, and we captured the forecasted future emissions, considering SaskPower is reducing our generation emissions as well over time. So by 2030, it is currently slated that coal would retire. So that would reduce emissions drastically in terms of everybody's electricity load. So you can see here, it's kind of an easy decision to add a heat pump, at least from an emissions point of view, for pretty much any scenario here. The natural gas heat pump does show some promise in that because it operates at all temperatures and it's 140% efficient, it tends to make up for some of the emissions, the higher emissions than a regular heat pump at the lower operating temperatures where you can't run a regular heat pump. So that's really interesting to me. I didn't realize that until Hadi informed me. So very cool. So annual emissions. So this is starting basically the end of last year today. It's a little bit different of a story, and this lines very well with Matt's presentation. So the natural gas heat pump right now, or the 95% natural gas furnace is a little bit better than the natural gas plus heat pump because our electricity emissions are higher. And obviously that changes by 2030. So the next maybe obvious question is, what does it do economically? And I think this is important for any residential or commercial customer, contractor wanting to potentially install these or inform customers. So right now, we looked at the, I guess, operating costs per year. This will change in the future. This is just current, and you have many other considerations. I won't go over them again. Matt went over them very well. But for the future, at this moment, if you install a heat pump on a 1980s two-story detached home, kind of that vintage of home, you're looking at a bit of an increase in your electricity bills and gas bills overall. About a $700 increase if you add a heat pump and run it down to -20. So operating conditions will vary. If you run it at a higher temperature, it won't do as much damage to your bills, I guess. For the other cases, SaskPower at least finds it very interesting. So all of our heating oil, heat pump, diesel, and other fuels, maybe even wood furnace, may benefit right now from installing a heat pump and having these as backup sources or supplementary sources. So it looks like you save quite a bit of money, you know, $1,700 per year if you go to a heating oil with heat pump, and about the same for the other technologies. So I think that's a great thing depending on the capital cost of the heat pump. I'm not going to repeat what Matt said again, but just to highlight, insulation and other home considerations are always, I think, most important other than the mechanical system. So considering these first is always recommended. I think it's a better bang for your buck and emissions that way. This graph we took from Electrification Canada, and CGA, I think, did a partnership thing here, but this chart I found really cool. So most of the operating range in the year is kind of 0 and above. If you see that here, and heat pumps will work, you know, down to -20, -23. So it does take care of the majority of the year if you wanted to install it. So they do work. I just want to highlight that. It's not anything odd here. You have to be careful on running it too low as per operating conditions. You don't want it to freeze up, but that won't happen as long as you follow manufacturer's directions. So I guess maybe the main question from SaskPower's point of view is, how does this impact our grid? There's a big difference in terms of, let's say, retrofit and new construction homes. So in retrofit homes, we have older things to consider. Some of our grid infrastructure is 50, 70 years old because they're just older neighborhoods, right?
Okay.
No, Scott.
The wonders of technology. So I'm going to turn it over to Clive right now and take it away.
Okay, let me work with the technology. Hello, everyone. Just going to work on sharing my screen so that you're able to see my presentation. Just give me a second while I work through this. So continuing with the Mitsubishi Electric Sales HVAC, residential HVAC division. And today, I'd like to share some information with you on air source heat pump technology, specifically referencing cold climate air source heat pump technology, and how this is applicable to residential retrofit, residential development within the Saskatchewan area. So you may very well know and have heard about heat pump technology. It's a technology that has been around for quite some time. Over the past several years, they've managed to improve the technology, with Mitsubishi being at the forefront of that development, where now air source heat pump technology can be used in many different regions in Canada as a primary heating system. But as you may know, there's a climate change or difference in temperature depending on the regions that you're in Canada. So looking at Saskatchewan, it gets very cold. And currently, air source heat pump technology may not be able to operate in those frigid winter temperatures of below -35, where you'd need some supplemental heat, even if you were to go to the extended range of air source heat pump technology. So bearing that in mind, the industry had looked at how can we incorporate this technology with the existing technology that can lead to greenhouse gas reduction, energy savings, et cetera, where homeowners could get the best of both worlds and have the ability to go all electric with this system if they so desired. It's a combination of a heat pump system that's integrated into an existing or new natural gas or electric furnace as an added system that provides heating as well as cooling. So that's one of the benefits of heat pump technology, is that from a single system, you're able to get both heating and cooling functions. Now, this system is applicable in different application, stemming from standard heat pump application or AC only application, or even single zone and multi-zone heating applications. Heat pump technology, it has been well known, and various studies have shown this, have shown air source heat pump technology to be one of the most energy efficient technology on the market. The downside with the technology has been that once the ambient temperature gets colder, the efficiency of the heat pump decreases. But in terms of the energy that is used to heat a similar space, a heat pump will take about almost 50% less energy than a natural gas furnace would use to heat the same space. So this is why integrating both technology can end up giving the homeowner the best scenario in terms of operating costs, where you will switch between the technology based on timing when it's most efficient to do so. Now, to assist with awareness and adoption of heat pump technology, the government is assisting financially with the adoption of heat pump technology targeting the residential sector, where across the country, you could get $10,000 for the replacement of an oil furnace system. You could get a maximum of 15 if you're out in the east. So for Saskatchewan area, there's very little to no oil that's being used for furnaces there. So this may not be a big incentive. But in terms of some of the utilities and federal program, there may be rebates available that can assist homeowners and developers with the use of heat pump technology. We see a growing demand and use of heat pump technology across the country. Looking at a summary of Canada Greener Homes grant for the past 3 years, they're seeing an average of 50 to 55% of the rebates that are submitted that are for heat pump technology, specifically air source heat pump technology. So the program is now closed, but there is approximately an estimated amount of 180,000 heat pump grants that are still left to be processed. So this just kind of highlight the growing awareness and acceptance of the technology amongst homeowners. look at what's available on the market. There's several different brands that are available on the market. Specifically looking at the Mitsubishi Electric brand. What is most important when we're using heat pump technology for heating our space is the heating capacity, because this is what the system is there for. It is there to provide heating to us in a more economical fashion and a more environmentally fashion. So the heating output at the low ambient temperatures are key in the performance of cold climate air source heat pump. And you could see that typically with a cold climate air source heat pump, it is expected to maintain 100% of its rating down to temperatures as low as -15. And you could have operating extension down to -35. Typically, once you get below -30, the efficiencies of the air source heat pump may be equivalent to that of electric resistance, where it's at 100%. And you may need to switch to an auxiliary heating source for the colder temperatures throughout the winter. But bear in mind, while that has been said, bear in mind that the coldest temperatures that we will see during the winter is 1% of the time. So 1% of the heating season would represent the coldest temperatures that you would see within the region. So basically, majority of the heating season, the heat pump system would run and can be done and can do so in a very, very economical fashion to the homeowner. This trend is growing, and Mitsubishi leads in terms of in-class products stemming from some of the major manufacturers that supply HVAC products. Amongst the major manufacturers, Mitsubishi is the only one having a add-on system that does qualify for the rebates. The add-on system is integrated into an existing furnace and can be retrofitted or used in new development. So for homeowners that may be looking at replacing their AC coil that's integrated into an existing furnace system, they can upgrade to a heat pump system and have the comforts of cooling and the energy efficient operation of the heating system, where maybe during the shoulder season, depending on how the homeowner may want to use the system, they may tend to use it as a secondary system, providing heating during the shoulder season. So pretty much fall and spring, and to some degree, the early parts of winter, depending on, how mild the winter is. But, based on outdoor temperatures, if it is not a very cold winter season, the heat pump can economically run throughout the heating season. In some of the coldest region in Canada, there's air source heat pump technology, specifically cold climate models, that have been used for primary as well as secondary heating systems. The system can be applied for multi-zone, where you may have a zone that's a ductless zone and you may have a ducted zone. In the ducted zone, you could add it on to the existing system and service also a ductless zone area where you're able to maintain separate temperatures within the space. With this system, it's not simultaneous operation, so it would be operation of either heating or cooling operation. Once you get up into the commercial line of product, those are the three-phase product, you are capable of doing simultaneous heating and cooling with air source heat pump technology. The technology is specifically driven by inverter technology, where you get variable capacity from the system. So many systems on the market today produces a variable compressor, providing variable heating output from the system. Mitsubishi system in particular has done a few different things that allows for comfort to the homeowner, the amount of time that it takes for the heat pump system to get up to ideal temperature that has been significantly reduced in comparison to a standard heat pump system. And you can see by the graph on the right, illustration on the right, it shows you the degradation of the heating output of a standard system in comparison to a 3-ton cold climate heat pump system. where you could see the rated heating capacity of 38,000 BTUs is maintained up until the point of minus 15 degrees Celsius. And there you'll get a drop off of the heating output, but not as sharp and not as significant as a standard heating output, as the systems sit somewhere at around the 75% mark of the total heating capacity that's available at the higher temperatures. Within a heat pump system, periodically the system may go into defrost to sort of melt any type of icing or frost buildup on the heat exchanger coil of the outdoor unit. Some of the previous heat pump system would just run this defrost cycle on an interval timing, regardless whether or not it is needed, as a means of ensuring that there's no ice buildup on the system. Over the years, the technology has improved. Mitsubishi has improved this certainly on their product, where we have limited the amount of defrost cycle by implementing what we call our smart defrost feature. So in essence, what the system does, it continuously monitors the heat exchanger to determine whether or not there is any frost development on the heat exchanger. And if frost development is there, it will engage the defrost cycle to get rid of the frost development and continue to monitor the system to determine whether or not there's frost development on the coil. So rather than just using an interval cycle, for example, that it would go into defrost every 2 hours, it uses our smart system to eliminate unnecessary defrost cycle. This is a improved application to air source heat pump in a hybrid application, where smart thermostat can be used for dual fuel switching, determining the ideal timing in which it is best suited to switch from heat pump technology operation to fossil fuel operation. And this is done in taking into consideration a few different factors that are built into the algorithm for switching. They look at the outdoor ambient temperatures, the efficiency of both heating system, the heat pump, and the furnace system, the outside temperature, what is the electricity rate and the gas rate at that given time, and then determine the efficiency and all of that combined to figure out exactly what is the ideal time to switch between the different technologies. And all of this is done seamlessly in the background, where the homeowner would just need to set the thermostat at the desired comfort temperature. We're able to achieve something similar in terms of a switchover, but not quite through this smart device, but through the programming of our remote controller. We can switch over between both operating systems. A few of the features that are available on the wired remote controller, where this can be connected wired or wirelessly, providing several different features. It can also be integrated into a third-party smart control device, such as, for example, a Nest or an Ecobee thermostat. Mitsubishi, as well as other manufacturers within the industry, does provide training on inverter cold climate technology. Mitsubishi has invested quite a bit in our training and our training equipment, and we do provide training nationally across the country. For the electrical connection of the system, this is a growing, sorry, I shouldn't say growing, because this technology has been around for well over 10 plus years, and the market as well as the industry has become quite familiar with how to install inverter type system, where power is supplied to the outdoor unit and it is then shared to the indoor control and indoor unit. There are safety prevention for water leakage that's caused through the buildup of condensation. We use a temperature sensor within the room, within the return air segment of the system, to try and give you a balanced temperature reading and ensure the comfort of the system. So multiple positioning in how the system can be installed. You're not typically limited through pipe length and height limitation for residential installation, as you do have a maximum of 245 feet and a maximum height of 100 feet, which when it comes to residential application, whether or not you're doing a single family or a MERB low to mid-rise application, these piping lengths are feasible within those applications. And that concludes my presentation this afternoon. At this point, if there's any question within the room, I am more than willing to take your questions.
Okay, we're running tight for time, so we're going to get right into the questions. So first off, I'm going to ask you if you have any questions. If not, we've got some questions for you. So yes, Jerry. You could, but what you're doing is you're really, because of the nature of the refrigeration, you're heating the air before it hits the coil. So it's going to make the heat transfer and the refrigeration cycle highly ineffective. Yeah, ideally, if you want to run them coincidentally, you have to have the A coil before in a preheat position, not in a reheat position. You guys have questions? You want to ask of the? First off, this is a non-technical question. It's meant more for the home builders and the contractors. And it seems to me that it would, you're going to have questions from your customers. And are there things that would help you in your communication with your potential customers? And what would that be? Crickets? Doug.
I have a question that since the report came out that the city was looking at a geothermal project building for Blairford to heat a new swimming pool, there's been a lot of confusion about where it comes from. So I think there's some confusion about ground source loops versus geothermal, especially in the city of Regina. I wonder if you could talk about vertical ground source loops. I know you had a bit on your presentation, you had to run through past. And so if you could erase some of that confusion, and is it still only vertical that makes sense, or if you could expand on that, how much room do you need?
Yeah, sure, for sure. So I guess we could distinguish two types of ground source. One would be like a deep geothermal where you're actually looking for higher temperatures. So I'm thinking of the well that is on the university campus that's a kilometer or two deep. So that's one type. For a residential application, we'd be looking at shallow. Usually instead of geothermal, it would be called like a geo exchange. So in that case, you could have vertical wells, which would maybe be sort of in the 10-meter range, or you could also have a horizontal loop, which sometimes could be like a slinky pipe, or it could be kind of lengths of loop that are laid horizontally or even directionally drilled. And so the amount of piping that you would need would be dependent on your heating load. I don't know the number off the top of my head, but a challenge in the city is just space, right? So if you have an urban lot, you're constrained for space. If you want to go horizontal, you're also constrained for access in terms of getting a drilling rig in to drill vertical boreholes, which is why we see ground source a lot more in the countryside, right? If you're on a lot with lots of room, there are some urban projects that have done ground source. Think of what is it now? Blanco Cantina, which used to be La Bodega. I think they've got a geothermal loop in there. But yeah, does that sort of address a little bit?
Yeah, the easiest way I think you can explain it to people is that deep geothermal, you're extracting heat from hot water deep in the ground. For shallow geothermal, you're using the ground as a battery and you're putting excess heat in when you're cooling, and you're extracting heat when you need heat. So, and the problem or the issue that needs to be addressed with shallow geothermal in our climate is that the balance for most weather-dependent buildings, there isn't a balance between cooling energy required and heating energy required. We're a net heating energy required. And with time, the Earth's temperature will decay to the point that you need to recharge it somehow. We have to recharge it with a small boiler that would trickle heat like a trickle charger. You could use solar thermal as the trickle charger for it, but you need to get the balance back. So there are large heat pump applications in the city. Most of them are old that use a heat rejector and a boiler, but they could have also been shallow geothermal. And those large buildings, if they have a large central non-weather dependent core, or they have a large heat generating device like a data center would be a perfect one, where you have the balance point between heating and cooling closer together, then you don't have to worry so much about the trickle charger. But if you're doing a geothermal installation, a geo-exchange installation, that's part of the process of design, is to figure out what that balance, heat energy balance is, and what you're going to have to do to accommodate it.
Hi, thanks. I've got a question actually for SaskPower, Sask Energy. Sorry, I forget your names, but I guess the first thing I'd like to say is I've been a very happy recipient of many of the programs that you highlighted. That being said, when you presented the information comparing the different cost and either carbon impacts or cost impacts, it seemed like it was very siloed in terms of considering what the homeowner or the individual client, small industrial, might bring in terms of their own self-generation. And obviously I'm talking about solar, and I also am aware that solar by itself is not an effective solution without storage. But that inflection point that Tom mentioned or Matt mentioned changes dramatically if you have a client that has some self-generation, even if it's not directly tied to the point where you need the heating input, but you've offset load. Excuse me. And I guess my question to you is there any interest or willingness to perhaps expand the program, perhaps look across the two crowns for where it may say, if clients were to invest in a certain amount of storage,
the video.
could you then offer some support for that? And would that then accelerate decarbonization and the adoption of some of these technologies? Thank you.
Yeah. Hello. Yeah, good. No, great question. Yeah, we've been doing, I guess, a few self-generation. I don't know if we're promoting it, but we're accepting it. I guess maybe that's the better word nowadays. So we used to rebate solar power many years ago. There was a rebate on the capital cost. And then there was, I guess a lot of people may not be familiar, but SaskPower has something called a marginal energy cost. So all that stuff that backs you up at night and everything when the solar's not running, that there's a cost to that. Right now at, I think it's 7.5 cents is the latest net metering rate. That's still probably close to double what SaskPower has to pay for maintaining, or it's paying the customers almost double of what we do. So there's still, I guess, a net benefit to the customers. So in some way, I guess SaskPower has chosen to still support it. The rates were reduced, but it still is a net benefit, I guess, to the customer on that end. In terms of grid storage, we're always looking at that. That's for sure something we're reviewing. I think SaskPower and Sask Energy together have a huge challenge. So Sask Energy more with the emissions side, because I don't know if they can lower their emissions down to a certain extent, right? Eventually SaskPower will be lower emissions just due to the nature of generating power and having clean, reliable sources available to us if we go down the trajectory we're going. So from SaskPower's side, our main issue right now is providing all the distribution transformation and the available generation to meet those needs. And providing customers with an affordable source of power is probably, I would say, number one, we want affordable, sustainable, and reliable power. But I think affordability is a key issue right now. And so a lot of these things we have to consider for programs. We're subsidizing one sector to take from another in a way, unless it benefits most of the people. So there's that balance there that we always have to look at. And I think self-generation and battery storage both hit that balance point where we need to look at that. So, I mean, SaskPower could also theoretically provide those emission reductions from the grid itself. So there's kind of a balance act between both. So we're trying our best to support that, support the adoption of electric vehicles, which help reduce things, and heat pumps we started looking into because these are the two, I guess, most prevalent technologies in emission reductions right now. And so we've chosen to focus mainly on those and then provide affordability-based programming. So I could see in the future potentially more support to that. Behind the scenes, we're doing analysis all the time. Does it make sense for us? Does it make sense to the majority of customers? Right now, batteries are still expensive, in general for a homeowner to put in. So that's one consideration. And I guess, from SaskPower's side, we're trying to align everything right now with federal programs as well. So the stackability is kind of a focus. But did that answer your question, or do you have a? We can talk after. I could go on for hours, but yeah, that sounds good. No, just want to say. Yeah, thank you.
Okay, further questions? In the back.
This one's for you, Matt. From your real world projects, what have you seen in terms of utility bills with the heat pump systems that have been put in compared to what you would expect for just conventional systems?
So maybe to start, the project that I showed the energy modeling from, we were seeing electrical bills in kind of middle of winter of like $400 a month type of thing, 400 to 500. Now that was a completely electric building, no gas service. That was hot water and also heat. And that was also during the months where we had that big cold snap. So average that out over the year, you could expect a lower average because in the summer it's going to be much lower. But yeah, that was sort of the peak month. Now that was a very efficient building. It was our 70 walls, our 96 roof, and our 40 foundation, and like pretty top of the line windows. So, but if you're building to that spec, then yeah, that's what they were seeing. So that's one example.
How
Yes.
big was the building?
It was 2-story with finished basement. I think it was like 2,400 square feet or something like that in Saskatoon.
And if you were going to compare that to conventional systems, is it kind of what the customer was anticipating, or were they happy, surprised? Any comments on that?
So they did start renting in the winter, and they were surprised with. So that's something that we talked about at the start during the design phase of the project was, hey, if you are fuel switching, the reality is that electricity costs a lot more than gas. And so they were surprised though. And so that's something that we had as a takeaway of further explaining that to customers. If you're fuel switching, gas is really cheap compared to power here in Saskatchewan. And so making sure that they're aware that just because you have a super efficient building and a super efficient heat pump, if you're shifting load from gas to electricity, you aren't going to see the sort of savings of like, oh, I bought a coffee and that paid for my heating for the month. So yeah.
Thanks.
Yeah, great question. Did you have anything you wanted to add? No, okay.
This is for the energy and power guys. 2030 for the elimination of coal. Realistic?
Yeah, a great question. So right now, I mean, we've shut down a few retired a few units. So Boundary Dam, part of it has been retired. I think SaskPower in general is still looking at things like carbon capture, and nuclear is obviously something we're participating in too. So I think those two things are highly dependent. Due to current regulations, we have to. So unless the federal government changes something in the Gazette or something in the future.
Yeah, percentage wise, if the curve, like the demand for electricity goes up, are you going to be able to meet that demand without burning more fossil fuels like natural gas?
Right. Yeah. Right now. So looking at renewables, I mean, the truth is it's not going to cut everything. It's not going to be able to fit that entire gap to fill it. So it'll have to be a combination of renewables and gas, obviously, and then maybe some extra nuclear if that is a thing. So I'm not part of that design group or anything like that, but I mean, we do have partnerships and we're looking at that for baseload technology. There's not too much hydro left in the province to meet that demand. So I'd assume, yeah, most of it would be
Yeah, right
gas.
now we're probably over 80% coal in that ballpark.
We used to be, now we're probably around 40%-ish.
Okay.
And then Boundary Dam 3, I guess you could count it, but it doesn't really count too much because most of the carbon's going in the ground anyway. So 80%
Yeah, I
up.
just wondered if the two curves would kind of line up when we hit the peak demand for electricity, will it be there?
Yeah, I mean, we're going to meet it. So not to get too into details, but we have to meet NERC reliability standards. So any peak that we expect, we have to be about 13% above that. And so we build out, we're planning already our next plants. You know, I'll say 5 years is pretty accurate, 10 years. So you're just hitting that mark where we're like, some decisions have to be made.
Sure.
And so I can't fully answer that, but I'm sure we'll meet it somehow. I'm not sure on the cost or anything at this point. Did you?
I just want to add on that consumption. So I think probably this is for 2023 or 2022. So the peak heating demand on natural gas side is 18 a gigawatt, and for electricity is 4 gigawatt. So that is a significant planning to shift all those heating load to electricity.
Yeah, like electrification could have a huge impact, but we're not seeing that mass adoption yet. But if EVs, everybody gets an EV and then everybody switches to heat pumps, that'll be a big issue. I can't see that happening immediately, especially due to the heat pump costs that we see, but I guess we'll see.
Question for the utilities. One of the most frequent questions we get from homeowners when we're sitting at the kitchen table discussing heat pumps is at what temperature does it make sense for them to switch from gas as primary to heat pump? And the Mitsubishi presentation alluded to an algorithm that they had for calculating that. Could SaskPower create that algorithm and put it on their website for homeowners to access that?
Yeah, so we put out our first bit of knowledge on our website. Maybe we can send a link out after or something. We're working on those other issues too to see what those temperatures may be. The heat pump selector tool that Matt alluded to before, I think that's a very good start. So we see a wide range of heat pumps from, you know, cold climate can go from -10 to, I think I've seen a -28 one that an actual company has recommended to operate. I think Clive even said -30-ish. So somewhere around that range is your stopping point. And I think the recommended heating temp, so that'll depend on emissions and economics. So each pump will have a different COP at different temperatures. And so on an individual basis, you could run it at any of those temperatures that it can operate on, but you'll want to look at what makes most sense, I think, financially. As you get to a higher temperature, you're going to be saving more money in disparity. So for example, above zero heating is going to be a lot cheaper on the electric side than below zero heating.
Yeah, just to further that, I mean, there's lots of manufacturers and lots of products for manufacturers. And with every different combination of indoor and outdoor units and configurations, they have different COPs. So I think that one thing that can help the resources and links you're going to see when you get Matt's slides will help you, because the Enercan will help in the sizing, but you might need to talk to somebody like Matt to figure out in the products, maybe products that you represent, because you know you don't represent all of them, but you could pick out, you know, the size that you're interested in, or a few typical sizes, and a few typical efficiency ranges, what those would be. So they're going to be close. I mean, we don't design watches in our industry. You know, we want to get close because the predictions done in a model are just that, predictions in a model. Real world's going to change. But I think all the resources are there. It would be helpful if SaskPower and Sask Energy could develop something that was kind of easy to use, but you could do it right now, and somebody like Matt could probably help you pretty easy. And I mean, almost all of the mechanical designers, certainly, or the energy auditors or modelers have access to that. It's open source and can apply it. So
right now, we're hesitant to put out too much information as well, because building code makes a huge difference on the sizing and selection. So if you have a brand new modern house, you're going to choose maybe an entirely different heat pump or group of systems than you would if you had an older home. And so right now we're just recommending to, talk to people in the know, do the sizing with contractors like Matt and other folks that are qualified. And we'll gradually put out more information, obviously, as time goes on here.
I just want to say it's going to be important that your sizing is more accurate than we're used to in this industry. Especially if you're doing a retrofit and you're looking at, they've got 120,000 BTU per hour furnace. And you find out that in the most extreme weather, it only runs half the time. It's way oversized. So you have to accurately size the appliance more accurately with heat pumps, I would say, than we're used to with gas furnaces and boilers. Because it's going to be very expensive if you oversize it, and it's not going to run efficiently all the time. And then once you have the accurate sizing, it's going to be easier to pick that point where the heat pump can't handle it anymore. And our cooling loads aren't nearly as big as our heating loads. So if you're sizing it for the cooling load, you're going to have to turn the furnace on sooner because your heat pump's smaller.
I can give you a real world example because I just went through the process. And being the engineer that I am, I made a spreadsheet. And so I came up with applying different sizes for my house, because it's a 1950s house that I've done all kinds of energy upgrades to, and it had a 1975 furnace in it. And so the furnace was oversized. So I right-sized my furnace, even with a little bit of wiggle room in there. And my air conditioner was oversized. And so I selected a heat pump based on cooling, because when I looked at the amount, the heating output, and the number of hours that it will eventually operate at, it made a negligible difference at the low end of the temperature scale. Most of the hours, the cooling capacity meets the heating capacity for the house easy. And so down at the low end, where you've got a lower COP, you've got a lower number of operating hours, and eventually no operating hours, heating with gas is much more appropriate. So, and by doing so, I also was able to use the same breaker that was in the panel, avoid the electrical upgrades that would be required. And it's overall, I think, is about the most economical installation in terms of life cycle cost. And, I'm going to run it as a heat pump for the first couple of weeks or whatever heating season's left. And then I'm going to shut it off. I'm going to run it as an air conditioner for 2 or 3 years, because I don't want to burn more carbon, emit more carbon than I would with a furnace. And then I'll make a decision based on what the cost and the actual carbon is a few years from now as to when I actually choose to operate it as a heat pump. By 2030, I expect, and I think the cost estimates that Matt used are totally reasonable, because the utility costs historically, although there's bumps along the way, have generally trended the way Matt has them projected. And by 2030, I think I'll both be in a position where if I'm not cost neutral, I might be a little bit of a cost benefit, and I certainly will be in a carbon benefit. So
I just want to also highlight in that Intercan air source heat pump sizing tool, one of the things that they give as a recommendation is when you're sizing, check, both that cooling and that heating load, and make sure that if you've got a unit, that it can modulate down low enough. If you're trying to size for additional heating, make sure it can modulate down low enough that it can still run at the cooling load without being too much oversized. So I think they recommend like a maximum of 125% of the cooling load, just because you don't want to run into a scenario where, yes, the heat pump can carry a lot of your heating load, but it's really uncomfortable cooling because it's oversized and so it can't actually cool properly.
Yeah, and as you guys that are in the industry know, an oversized piece of cooling equipment doesn't have good humidity or dehumidification control because it's cycling on and off all the time. It beats itself to death because it's cycling all the time, even with the new compressors that are variable speed. And so you're going to get, a shorter lifespan out of that piece of equipment, and you're going to have a spiky humidities and temperatures if it's terribly oversized. So. Back.
Thank you. Given the complexities of like right sizing a system or a home load, and given the fact, it seems to me that a lot of homeowners, when they are upgrading their furnace or HVAC system, they do it under the duress of a no heat or a no cooling call, right? A vast majority of system upgrades happen when they abruptly reach end of life, and they might not have the bandwidth to navigate like complex programs and design a system, right? And so we might be leaving a lot of opportunities for switching to heat pumps on the table because people are making these purchasing decisions under an emergency situation. So what suggestions, given your experience, the experience of folks presenting today, what pathways do you see for homeowners who have to make such decisions?
Well, personally, I feel that the opportunity and the obligation really rests with the mechanical contractors, because you are the front line in the residential sector. 95% of people will go to a mechanical contractor first. And that's why we want you guys to be as informed as you can, so you can have those conversations. Like, we're not saying do one particular thing, but we're trying to get everybody informed so that you can understand the options that are available for their customers, answer their questions, and provide valuable feedback to them so they can make an appropriate decision. I mean, there's other marketplace considerations, particularly when you're in that kind of emergency situation. But if you're doing maintenance on a piece of equipment with your customers, because often you're called in to do seasonal maintenance, it's the opportunity to have a conversation with a customer about, hey, you might want to consider upgrading before you do get into an emergency situation. And then it's a potential sale for you. So there's the benefit to it, but you're also providing your customer with the best information possible. So, and I think in the new home market, certainly the developers and the general contractors in the new construction market are another easy path into it. So, I think if our work with the Home Builders Association, they understand that, but it's a big industry. We have lots of players in it. And trying to get everybody kind of up to speed, and things have been changing. I mean, the utilities are dynamic, the rebates programs are dynamic, the equipment and technology continues to evolve over time. And so, there's not one easy answer, one size fits all. Any other questions?
Question that I had and I've heard is, we know heat pumps have been around for a while. So what's the difference between an air conditioner and a heat pump?
Not much. A valve and some pipe. So a refrigeration cycle moves heat by using a compressor, some pipes, an expansion device, and 2 heat exchangers. That's a refrigeration cycle. And then if you're moving the gas and the liquid in one direction, it's moving heat from lower temperature side to a higher temperature side, and through the reversing valves or the other switching technology, it's just reversing the operation. So it is the same device, it's just which direction it's moving heat.
So if I'm buying like an air conditioner, I can get just a standard air conditioner, or I can get a heat pump. The heat pump just has the ability to go both ways.
Correct.
In terms of cooling
That's a
efficiency,
really simplistic explanation.
Yeah.
I mean, there's other things that go into it. Clive alluded to the fact that, you know, in a cold climate, you have to accommodate defrost, and like there's the devil's in the little details, but yes, it is essentially the same technology.
and from a cooling efficiency point of view, if I'm looking at getting just an air conditioning unit, standard air conditioning unit, or the heat pump version, is the heat pump like newer technology that has higher COPs, or what are we seeing out there?
It's like all devices that use energy, there's a range of efficiencies in everything. So there's a range of efficiencies in air conditioners. So you see their seasonal efficiency ratings labeled on, and they could be anywhere from, I don't know what a typical SEER is, like 12 or something like that. So you can get a SEER 22. It's just got a giant condensing unit to get that kind of efficiency. Same with heat pumps. You can get a range of efficiencies. Even I suspect in Mitsubishi's line, they have ranges of efficiencies depending on what product you're using. And that what was stated earlier, like Jerry said, though, a lot of it has to do with the conditions that it sees. So, you know, if what the temperature differential is between the heat source and the heat sink makes a huge difference in efficiency, because it's the amount of refrigerational lift, we call it, the amount of compression, the amount of work they have to put into the compressor to make the heat move changes. But so, yeah, you can get, but the modern, let's call them Camrys, not Cadillacs, but the Camrys, they're going to be more energy efficient than say a 20-year-old air conditioner that you have in your house, just because the products evolved over time. So more efficient compressor, better condenser design. Other questions? Well, if not, I'd like to thank first off all our presenters and for taking the time, and of course you. I'd like to reiterate my thanks to the University of Regina, the Faculty of Engineering, the Office of Sustainability, and the VP of Research. I'd like to thank the City of Regina again, and of course SaskPower, Sask Energy, and our presenting partners, the Home Builders Association and the Mechanical Contractors Association. So we will endeavor to send out a link to the presentations and the recording in the next couple of weeks. Not sure exactly when it will go out, but as soon as it gets posted on the U of R Faculties of Engineering's website, we'll make sure we get the links out to you. So thanks, and have a great day. Thanks, Clive.
Thank you very much, everyone. Thank you.